Hello, I'm Slumbo, Soy Technical Courage. Welcome to another discussion of the Construction Technician series. And today we're going to look at applied scientific techniques. And applied scientific techniques comprises of mechanics, science and materials, and construction and mathematics. And this subject is written as the multiple choice paper. So today we'll be looking at stress. In as far as mechanics is concerned, stress is defined as the force per unit area. In most cases, the effect of force acting on an area can be determined only by calculating the stress produced. So the formula for determining the stress is force over area, where force is in newtons and the area is in square meters. The units of stress, you can also have alternative units of stress depending on the magnitude of the figure that you are calculating. You have newtons per square millimeter, and newtons per square meter, kilonewton per square millimeter, or kilonewton per square meter. 1 Pascal is equivalent to 1 Newton per square meter. So like what we are saying, that to work out stress, we have to divide the force over area. So we have this object here which shows the hatched. This hatched part is the cross-section of the object which is under tensile force. So you need to know this cross-sectional area by multiplying the breadth times the length, and then you have the area of the cross-section of the object. And also the force is normally given, so you divide force in newtons by the area in square meters. However, if this is under compression, then the force will be acting against each other, like what we say. So we can see that the force are pointing towards the object as opposed to the area object that we had, where the forces were pointing outside. We're pointing away from the object. So let's look at an example. A column measuring 400 millimeters by 400 millimeters by 4 meter high supports a load of 500 kilonewtons. Find the stress at the top of the column in newtons per square millimeter. So what we need in this question, we first of all need to find out, to work out the cross-sectional area of the column. So the cross-sectional area of the column, since we've been given this measurement 400 by 400, so we say 400 times 400, then the answer is going to be 160 square millimeters. We've been given the force or the load, which is 500 kilonewton. Since we've been asked to work out the answer in newtons per square millimeter, and then we are going to multiply 500 kilonewton times 1000, so that we convert kilonewtons to newtons. In fact, kilo means 1000, so that's why we are multiplying by 1000. So this value divided by 160,000 square meters, then it gives us the answer, which is 3.125 Newton per square millimeter. Another area that we need to discuss is the strain. So whenever the force is under stress, the result that you get is the strain. It's either the object will break, or either the object will deform in shape, or it will disfigure in one way or the other. So we say that is the strain. So this is the linear strain that we are looking at. So it's defined as a ratio of change in length of a material to its original length. So you look at the change in the material and you compare it to the original length. So a building material deforms when a significant amount of force is applied on it. A tensile force causes elongation of the material, but a compressive force will cause shortening. So it's like you are compressing something, you are squeezing, it's like squeezing, you are reducing the shape. So it reduces in size. That is, when the object under a certain stress, then the compressive force, or maybe compressive stress, it has to shorten in its size. But where it results in elongation, just know that the forces were acting away from the object, that is tensile force. So we say the object is under tension. So for a constant volume of a material, the change in length is accompanied by the change in the cross-sectional area. So to determine the strain, we say change in length or elongation, or you subtract the new length minus the original length over the original length. So if the answer is negative, just know that the object was under compression. But if you have a positive value, then the object was under tension. So we use the Greek symbol for strain, which is the epsilon, as what you have there. So strain may be tensile, compressive, or shear. So tensile strain occurs when there is an increase in the original dimension. Compressive is when there is a decrease in the original dimension. So strain is measured as a percent, or we say strain does not have the units. So let us look at this example. A metal rod is subject to an axial tension which causes a strain of 0.08%. If the original length is 500 millimeters, what is the change in length? Or in other case, what is the elongation? So if we look at the formula, we have change in length or elongation over the original length is equal to the strain. So we've been given the strain, we've been given the original length, but we do not have the elongation. So we need to work out the elongation. So you substitute the values that we've been given into the equation, like strain is 0.08, and change in length is the one that we are finding. Since we are expressing this as a percent, we multiply by 100, and then you have 500 millimeter as the original length. So transposing the figures, making change in length the subject of the formula, then we have the strain times the original length over 100. So that gives us 0.4 millimeter. So it means that in this case our elongation is 0.4 millimeter. So this is our elongation. So if we consider looking at another example, a specimen of steel measuring 150 millimeter in length was tested in compression under a load of 20 kilonewton. The final length was 145 millimeter. Find the strain produced. So if we look at this problem, we have the original length, we have the load applied on the object, and then we have the final length. Then we are supposed to find the strain produced. So for us to determine the strain, we need to have the change in length, okay? And also we need to have the original length. So since we have a specimen of steel measuring 150 in length was tested in compression under the load of 20 kilonewton, the final length was that one. So which means in this case 20 kilonewtons is there just to give us a picture, but not necessarily that we are going to use it in our equation. What we use is 150 and 145. Those are the figures that we will need in order to work out the strain. So like I said, strain is change in length over original length. So the original length is 150. Since we've swapped, it was supposed to be the final minus the original, which is in this case it was going to be negative, which is compression anyway. So since we already know that it's going to be compression, since we have a reduction in the original length, so it's going to be compression. So we say 150 minus 145 over 150, and that gives us 0.03 0.33. So since we've said strain is unitless, so you don't have any units there. So we can express this by multiplying. If you want to express it as a percent, we multiply by 100, and then it becomes 3.3% as our strain. Yep. So let's consider the Young modulus of elasticity. All solid materials will change shape slightly when stressed. If a material reverts back to its original shape and size when the stress is removed, it is an elastic material. But then the Young modulus is the toughness of that particular material, how tough the material is, how strong the material is. That is the Young modulus. So those that have got higher Young modulus, it means that that material is stronger as opposed to the ones that have got a lower modulus. So the Young modulus E is represented by the letter E, is the stress per unit strain. In other case, we divide stress by the strain to determine the Young modulus, like what we have. So since the strain is unitless and the stress have got the units in form of newtons per square millimeter, so the Young modulus will take the units of the stress. So the basic units, of course, is the newton per square meter. That's the basic, but you can have other units in that format. So let's look at an example. A metal rod of 14 millimeter diameter has an initial length of 1.0 meters. After a tensile force of 12 kilonewtons was applied to the rod, its length increased to 0.006. Calculate the Young modulus. So what we need in this case is, we know that Young modulus is stress over strain. So we need to know the value of stress, we need to know the value of strain for us to move forward. Otherwise, we may not be able to work out. So to calculate the value of stress, we need to determine the cross-sectional area of this metal rod, which has got a diameter of 4 millimeters, and the force has already been given. Then we can work out this. But as for the strain, we have the original length, and also we have this as our final length. So we can find the difference and divide by the original length. We have the stress in that case, sorry, the strain. So our solution, like I said, cross-sectional area of the rod. So since the rod is circular, it has a circular cross-sectional area, then we use the formula pi r squared, where r is equal to 14 divided by 2. Since we've been given 14 as the radius, so we are saying 14 divided by 2, which is equal to 7 millimeters. But if you had wanted to use the same diameter without dividing by 2, we could have said pi area is equal to pi d squared over 4. It's the same, you still get the same answer. So our area in this case, since we have pi is equivalent to 22 over 7, then we multiply by 7 squared, which is the radius of the metal rod, and it gives us 154 square meters. So we have the area for all that. And then to work out the stress, so we say force over area. Force, we have 12 kilonewtons, so we multiply by 1000, so that we have 12,000 newtons and not kilonewton, because we want it to be in newtons, and divide by 154. So this gives us 77.92 newtons per square millimeter. So we are done with the stress, and then the next is to work out the strain. So the strain is you have the final dimension, which is 1006 millimeter and 1000 millimeter. So you divide this. Of course, when you are working out these problems, they need to be all the same unit. If we had wanted, we would have converted them to all meters, so they should have been meters only. But in this case, we are interested in using the millimeters, so that's why we've multiplied by 1000 wherever we had meters. and the answer would be the same. So we have 1006 minus 1000 over 1000, it gives us 0.006, because if we subtract here, the answer is 6 over 1000, then that's the answer that we get. So since we have the strain, we have the stress, we can easily work out the Young modulus, so which you say 79.92. This is Young modulus is stress over strain, so 79.92 over 0.006, and it's in newtons per square millimeter. So the Young modulus is going to be 13,320 newtons per square millimeter. So that's the answer that we get. But also we may need to know the relationship between the stress and strain. That is, we can plot a graph of showing the relationship between the stress and the strain. If we increase the stress in the object, what will happen to its strain? If we reduce the strain, what will happen to its stress? That is, what will be the value? So in most cases, you increase the stress, and what will be the strain? What will be the result? If you increase the loading, what will be the result? So that's how. That's what we have here in the figure. So it's a graph of stress against strain. So as you would see in this case, you see that the graph from 0, 0, it goes straight until it reaches P. And there it curves a little bit, then you have E, and it goes like that. So P is the limit of proportionality. So you can see P is the limit of proportionality, whereas for limit of proportionality in this case, we mean to say that whatever you are doing to the stress will give the same the proportion, in proportion will give the proportion results to the strain. So that's what it means in this case. But after you reach point P, then the object starts disobeying. It may not necessarily follow that rule because the graph now is starting to bend. And point E is the elastic limit. So after the limit of proportionality, the curve is no longer a straight line, but the material still behaves as if behaves as an elastic material up to a point known as the elastic limit. So elastic material, when we say the material is elastic, we mean the material can go back to its original shape after you remove the load. So you apply the load, it will deform, but you remove the load, it will go back to its original shape. So that's the elasticity in that case. That's what we can say. So after the loading, that is further loading after E, the sample shows plastic behavior whereby the extension produced is not proportional to the loading. So after E, the material is showing the plastic property. That is, you have the plastic range anyways, plastic stage here. When we say something is showing the plastic property or plasticity, or something is plastic, we mean to say that if you bend that material, it will maintain that shape without going back to its original, maybe in a straightened shape. For example, you may bend a metal maybe into with a 90-degree angle. If it doesn't go back, then we say it is plastic. But you cannot bend a rubber and thinking that it will remain in that shape. It will easily go back to any other shape because it's flexible and whatever. But for something that is plastic, it will bend, would not go back to its origin. So any point after E, then the object starts behaving in a plastic manner. That's what we have. So at point Y1, the upper yield, the material will flow, deform. That is, the material will deform even if the load is reduced slightly. So in this case, since at first you are putting a load or whatever, you are putting a load and then it extends in proportion and but it reaches a point after the elastic limit. Even if you add very little amount of the load, it will have a bigger impact or it will show a bigger strain. If it is extension, it will extend even more than it was doing before, because it has lost its elasticity. So that's the upper yield, and of course the C is the lower yield point. So at the lower yield point, the material regains its resistance to deforming force. The extension increases at a higher rate due to further increment in the force. So at the lower yield point, it's like the material has regained partly its resistance to deforming. It may not necessarily deform, so the extension increases at a higher rate due to further increment in the load. In that case, that is at Y2. U is the maximum, that is the ultimate stress. So U is the maximum load applied and is called the ultimum stress. The length of the specimen starts to increase considerably with a reduction in the diameter of the sample at the round. So assuming that you are using a circular or whatever which has got a diameter maybe 20 millimeters, so at U you have even the diameter reducing. Instead of having 20, it becomes maybe 18, 16, 12, and so on, until it fails at F. So at F, that's where the object now fails. So the object fails at F. Here, the object fails here. Okay. In other case, when we are saying the object has failed or the object has yielded, we mean it has broken. If it is a bridge, then it falls. If it is whatever, then you have it divided into two parts. That is we say something has failed. So thanks for your attention. Maybe as a follow-up to see how you have fared in this lesson, you should try the following, and you submit the exercises to me. Maybe in 2 weeks time I would need the exercises submitted. So one of the questions is: a concrete cube of size 150 millimeter is tested in compression where the failing load was 90 kilonewtons. Calculate the compressive stress at the failure point. And the other question: a steel bar of a rectangular cross-section that is 20 millimeter times 30 millimeter subject on an axial pull of 60 kilonewton. Calculate the tensile stress on the bar. Another: in a test on a machine, a strain gauge was attached to a steel column having an area of 5026.55 square millimeters. What is the tensile load applied when the gauge indicated 1.8 times 10 to the power minus 6? So modulus of elasticity for steel is 2010 kilonewton per square millimeters. You also have calculate the stress in a circular bar with 10 millimeter diameter subject to a force of 15 kilonewton. So you try these questions and see how you have fared. Any challenges, they should be addressed to me.